Hi, welcome to our new topic Geometrical Isomerism in Alkenes. Here Dr. Sridevi is presenting you about the isomerism in alkenes. Before going to the geometrical isomerism, here we will see the definition of stereoisomerism. In stereoisomerism, the isomers have the same molecular formula and the same structural formula but differ in spatial arrangement of atoms in the molecule. There are two types of stereoisomerism. First one is geometrical isomerism and the second one is optical isomerism. Now let us see what are geometrical isomers. Geometrical isomers occur in organic molecules where the rotation around a bond is restricted. This occurs most often around C double bond C. The most common cases are around asymmetric non-cyclic alkenes. The carbon-carbon double bonds are made up of a S and a P bond. The P bond is formed from the combination of two P orbitals, one from each of the two carbon atoms. The two P orbitals must be in the same plane to combine. Now let us see the geometrical isomers in alkenes. In alkenes, two carbons are linked through sigma bond and a pi bond due to the overlap of p orbitals. In such compounds, these two carbons along with four substituents remain in a plane and are locked because rotation will break the double bond. This restriction of rotation is responsible for the geometrical isomerism in alkenes. C double bond C bonds have restricted rotation, so the groups on either end of the bond are frozen in one position, and it is not easy to flit in between the two. Here we have given a structure which is showing the free rotation on the right hand side and a restricted rotation on the left hand side. On the right hand side, if there is a single bond, there is a free rotation. On the left hand side, as there are two knots or two bonds, which makes the rotation restricted. Here you can see an example or a structure of alkene. Here the black ball represents carbon, white ball represents hydrogen, and the green ball represents any group like alkyl, ethyl, methyl, or any other alkyl groups. So here it is a structural representation or a ball model representation of alkene, which have a restricted rotation. This structure produces two possibilities. The two structures cannot interchange easily, so the atoms in the two molecules occupy different positions in space. You can see in the left side structure, there are two green atoms or two green balls towards one side and two white balls towards the other side. But in the right hand side structure, you can see there is one green ball and one white ball on one side and other green ball, other white ball on the other side. But this kind of rotation is not so easy or not possible in case of double bonds like alkenes. When we consider the example of 2-butene, it exists in two spatial arrangements, cis-2-butene and trans-2-butene. Such compounds are referred as geometrical isomers. A cis isomer is the one in which the substituents are on the same side of carbon-carbon double bond. Here you can see two methyl groups are on one side and two hydrogen groups on the other side. A trans isomer is a one in which the substituents are on opposite sides for C double bond C. You can see here there is one hydrogen atom and one methyl atom on one side and one methyl atom and one hydrogen atom on the other side. This makes this compound trans, and the cis isomer and the trans isomer are examples for geometrical isomerism. Let us see the other example. There are three structural isomers for C4H8 that are alkenes. C4H8 is nothing but butene. So we can have four isomers for butene. It is but-1-ene, trans-2-butene, cis-2-butene and 2-methylpropene. Of these, only one exhibits geometrical isomerism. That is, but-2-ene exhibits geometrical isomerism. It can exist as cis form also in the trans form. Now let us see what are the properties of geometrical isomers. Trans alkenes, which are less polar and more symmetrical, have lower boiling points and higher melting points. And the cis alkenes, which are generally more polar and less symmetrical, have higher boiling points and lower melting points. Here there is an example of 1,2-dichloroethene. It exists in two forms, cis 1,2-dichloroethene and trans 1,2-dichloroethene. Cis 1,2-dichloroethene is having a boiling point of 60 degrees centigrade, whereas the trans 1,2-dichloroethene has the boiling point of 48 degrees centigrade. In cis isomer, we can observe there is an intramolecular hydrogen bonding. Here, if you see the structures of trans-but-2-ene 1,4-dionic acid and cis-but-2-ene 1,4-dionic acid, you can see the melting point on the left-hand side structure, that is the trans structure, is 286 degrees centigrade. And the melting point on the right hand structure, that is the cis structure, has the melting point of 130 to 131 degrees centigrade. Here we can see there is a variation in the melting point because of intramolecular hydrogen bonding. The cis isomer on heating undergoes chemical reaction, whereas the trans isomer doesn't react chemically. Here is an example where cis-butene-dioic acid, when heated at 160 degrees centigrade, it is getting converted into furan 2,5-dione. But the trans-butene-dioic acid, when it is heated at 160 degrees centigrade, it is not getting converted. That means it is not undergoing any chemical change. When we come across the pharmaceutical applications, the industrial synthesis of fumaric acid proceeds via cis-trans isomerization of malic acid. The left-hand structure, fumaric acid, is getting converted into the right-hand structure, malic acid. Fumaric acid is a cis form where you have both COOH groups on the same side. But in the malic acid, the both carboxylic groups are on opposite sides. Usually, the trans form is more stable than the cis forms because in the trans form, the bulky groups are on opposite sides, and in the cis form, you have the bulky groups on the same side. And always the bulky groups will cause steric hindrance, which is not faced in the trans form but faced in the cis form. Here we came to the end of our topic, geometrical isomerism in alkenes. Thank you.